So in mechanics, to discuss the motion of a particle in a plane, we choose a two coordinate system, a two-dimensional coordinate system. Yx is the x-axis, Oy is the y-axis. The position of the particle in xy plane at any instant are described by the Cartesian coordinates x and y. The direct line segment OP bar is called as the position vector of the point P. The position of the particle at any instant is described by means of this position vector. The direction of the position vector of the particle is taken from the origin towards the particle. The magnitude of the position vector gives you the distance of the particle from the origin. You can drop a perpendicular from the point P on x-axis. Similarly, you can drop a perpendicular from the point P on y-axis. So A is the foot of the perpendicular dropped from the point P on x-axis. B is the foot of the perpendicular dropped from the point P on y-axis. So in the figure, the length of the line OA, as you know, we call abscissa or x-coordinate. The length of the line OB, we call it as ordinate or y-coordinate. So OA PB is a rectangle, and every rectangle is also a parallelogram. So from parallelogram law of vector addition, we can write vector OP bar equal to OA bar plus OB bar. In general, any vector can be expressed as the product of its magnitude and the unit vector in the same direction. The unit vector along positive direction of x-axis, as you know, is denoted by I bar or I cap. The unit vector along the positive direction of y-axis denoted by J bar. Any vector can be written as product of its magnitude and unit vector in the same direction. So vector OA bar can be written as OA into I cap. Similarly, vector OB bar can be written as OB into J cap. So the direct line segment OP bar can be written as OA into I cap plus OB into J cap. Now I can write the length of the line OA equal to x, length of the line OB equal to y. That means the position vector of the point P, which is denoted by R bar, can be written as x into I cap plus y into J cap. Therefore, in general, the position vector of a point P with the Cartesian coordinates x comma y in the xy plane is given by r bar equal to xi cap plus yj cap. So the direction of the position vector of the point P is taken from the origin toward the point P. And magnitude of the position vector of the point P gives you the distance of the point P from the origin. So in the figure, length of the line OP or magnitude of the position vector r bar can be written as root of x square plus y square. So in a three-dimensional coordinate system, suppose if x comma y comma z are the Cartesian coordinates of a point P with respect to origin O, then the position vector of the point P with respect to the origin O, which is denoted by r bar. The direct line segment OP bar is called position vector of the point P, denoted by r bar. That can be written as I cap into x plus j cap into y plus k cap into z, where k cap is the unit vector along the positive direction of z-axis. The magnitude of the position vector of the point P gives you the distance of the point P from the origin. That means mod of r bar is equal to length of the line OP, which will be equal to root of x square plus y square plus z square. Next, I am going to discuss how the displacement of a particle can be expressed in terms of its position vectors of the initial and final positions of the particle. Let us suppose a particle is displaced from a point P to another point Q. Let xi, yi, zi denote the Cartesian coordinates of the initial position of the particle and xf, yf, zf denote the Cartesian coordinates of the final position of the particle. Let O be the origin of the fixed coordinate system. Now the direct line segment OP bar represent the position vector of the initial position of the particle that I have denoted by Ri bar. The direct line segment OQ bar represent the position vector of the final position of the particle denoted by RF bar. The magnitude of the displacement of the particle is the shortest distance between the initial and final positions. That means the length of the line PQ gives you the magnitude of the displacement of the particle. The direction of the displacement of the particle will be along the straight line PQ from initial position P toward the final position Q. That means here PQ bar represents the displacement of the particle, which can be denoted by S bar. The director line segment OP bar represent the position vector of the initial position of the particle, denoted by RI bar. As I just discussed before, in general, the position vector of a point with Cartesian coordinates x comma y comma z is given by r bar equal to I cap into x plus j cap into y plus k cap into z. So now the position vector of the initial position of the particle can be written as I cap into xi plus j cap into yi plus k cap into zi. Similarly, the director line segment OQ bar represents the position vector of the final position of the particle, denoted by RF bar, which you can write I cap into xf plus j cap into yf plus k cap into zf. So in the given figure, the figure I have drawn on the left side, from triangle law of vector addition, you can write vector OP bar plus PQ bar. You can observe in the diagram that head of the vector OP bar is attached to tail of the vector PQ bar. So the two vectors OP bar and PQ bar, they are in the same order. The vector OQ bar is in the reversed order. So from triangle law of vector addition, we can write OP bar plus PQ bar equal to OQ bar. Or you can write PQ bar equal to OQ bar minus OP bar. Now the direct line segment PQ bar represents the displacement of the particle in vector form. The direct line segment OQ bar represents the position vector of the final position of the particle, denoted by RF bar. The direct line segment OP bar represents the position vector of the initial position of the particle, denoted by RA bar. So you can write the displacement vector of the particle is given by S bar equal to RF bar minus RA bar. So in many numerical problems, we directly write this step. So displacement of the particle in vector form, we write position vector of the particle in the final position minus position vector of the particle in the initial position. Now RF bar can be written as I cap into xf plus j cap into yf plus k cap into zf. And Ri bar can be written as I cap into xi plus j cap into yi plus k cap into zi. So the displacement of the particle in vector form can be written as I cap into Sx plus j cap into Sy plus k cap into Sz. Here Sx represents the x component of the displacement of the particle, which will be equal to the x coordinate in the final position minus x coordinate at the initial position. Sy is the y component of the displacement of the particle, which you can write y coordinate in the final position minus y coordinate in the initial position. So Sz represents the z component of the displacement of the particle, which you can write z coordinate in the final position minus z coordinate in the initial position. So displacement of the particle in vector form can be written as S bar equal to I cap into Sx plus j cap into Sy plus k cap into Sz. The x component of the displacement denoted by Sx can be written as x coordinate in the final position minus x coordinate in the initial position. The y component of the displacement of the particle is equal to the y coordinate in the final position minus y coordinate in the initial position. Sz represents z component of the displacement of the particle, that you can write z coordinate in the final position minus z coordinate at the initial position. So as I was discussing the displacement of the particle in vector form. So in vector form, the displacement of the particle we have written as S bar equal to I cap into Sx plus j cap into Sy plus k cap into Sz. The magnitude of the displacement of the particle will be equal to the magnitude of the displacement of the particle will be equal to the shortest distance between the initial position P and final position Q. That means equal length of the line PQ, which we just write letter S without the bar symbol. It represents the magnitude of the displacement of the particle, that you can write under root of Sx square plus Sy square plus Sz square. Sx equal to the xf minus xi. Sy equal to yf minus yi. Sz equal to zf minus zi. That is the same formula will be discussed for mathematics students in elementary coordinate geometry for finding the distance between 2 points. So next I would like to once revise what I have discussed about the position vector and displacement vector, and those who are interested to write the notes they can take the notes from the PowerPoint presentation, which I'm going to show you now. And wherever you want to write the notes systematically, you can take a pause and write the notes. Look at the screen once. So once we revise the earlier discussion about position vector and displacement vector. So in three-dimensional coordinate system, the position vector of a point P with coordinates x, y, z with respect to origin O of the coordinate system is given by OP bar equal to R bar, that can be written as I cap into x plus j cap into y plus k cap into z. The direction of the position vector R bar of the point P is from the origin O toward the point P. The magnitude of the position vector gives the distance of the point P from the origin. That is the length of the line OP, or mod of R bar can be written as root of x square plus y square plus z square. Next, we discuss about the displacement of the particle in vector form. Let a particle be displaced from the point A with coordinate xi, yi, zi to another point B with the Cartesian coordinates xf, yf, zf as indicated in the figure. This is the initial position of the particle. This is the final position of the particle. This OA bar represents the position vector of initial position of the particle denoted by RI bar. The direct line segment OB bar is the position vector of the particle in the final position, which is denoted by RF bar. From triangle of addition vectors, we can write OA bar plus AB bar equal to OB bar. Or you can write AB bar equal to OB bar minus OA bar. So displacement vector of the particle is equal to the direct line segment AB bar, which is denoted by S bar. That you can write RF bar minus RA bar. Means position vector in the final position minus position vector in the initial position. RF bar is written as I bar into XF plus J bar into YF plus K bar into ZF. RA bar is written as I bar into XI plus J bar into YI plus K bar into ZI. This can be written as I bar into XF minus XI plus J bar into YF minus YI plus K bar into ZF minus ZI. Or we write S bar equal to I bar into Sx plus J bar into Sy plus K bar into Sz. Where Sx can be written as Xf minus Xi, Sy equal to Yf minus Yi, and Sz can be written as Zf minus Zi. Magnitude of displacement vector equal to length of the line AB. That is written as mod of S bar is equal to root of Sx square plus Sy square plus Sz square. Can write Sx equal to Xf minus Xi, Sy equal to Yf minus Yi, and Sz equal to Zf minus Zi. So magnitude of displacement can be written as root of Xf minus Xi whole square plus Yf minus Yi whole square plus Zf minus Zi whole square. look at one problem I am going to discuss based on the discussion we have just done. A particle is displaced from the point 5 centimeter, comma 7 centimeter, comma 10 centimeter to another point with coordinates -1 centimeter, comma 2 centimeter, comma 15 centimeter with a constant velocity in a time interval of 5 seconds. Find the velocity vector of the particle. So you can look at the solution of this problem. So here the particle is first displaced from one point, I have denoted by A, with Cartesian coordinate 5 centimeter, comma 7 centimeter, comma 10 centimeter. To another point B with Cartesian coordinates -1 centimeter, comma 2 centimeter, comma 15 centimeter. The particle moves from A to B with constant velocity in a time interval of 5 seconds. So displacement vector of the particle is equal to I cap into Sx plus J cap into Sy plus K cap into Sz. So x component of the displacement of the particle denoted by Sx is equal to x coordinate in the final position minus x coordinate in the initial position. Here x coordinate in the final position is -1 centimeter. X coordinate in the initial position is 5 centimeter. So this comes out to be -6 centimeter. So the y component of displacement of the particle is equal to the y coordinate in the final position minus y coordinate in the initial position. Here the y coordinate in the final position is 2 centimeters. Y coordinate at the initial position is 7 centimeters. So that comes out to be -5 centimeters. Similarly, that component of the displacement of the particle denoted by z can be written as z coordinated in the final position minus z coordinated in the initial position. That is 15 centimeter minus 10 centimeter. That will be equal to 5 centimeter. So displacement of the particle in vector form can be written as S bar equal I cap into Sx plus J cap into Sy plus K cap into Sz. So here Sx equal to -6 centimeters. Sy equal to -5 centimeters. Sz equal +5 centimeter. So when a particle moves with constant velocity, we can write displacement vector is equal to velocity vector into time interval. Or you can write the velocity vector of the particle is equal to displacement vector of the particle divided by time interval. So thus you can write as -6i cap minus 5j cap plus 5k cap centimeter divided by time interval is given as 5 seconds. So you get the answer as minus 1.2 I cap minus j cap plus k cap centimeter per second. That's the answer. In case you want to copy the solution, you can take a pause and copy the solution. So next, I am going to discuss the condition for collision of two particles. When you are given the position vectors of the two particles and the velocity vectors of the two particles at the initial positions. Let us suppose R1 bar is the position vector of one particle. Let R2 bar denote the position vector of another particle at a particular instant. That means one particle is at the point A with position vector R1 bar. At the same instant, the second particle is at the point B with position vector R2 bar. What is the origin of the coordinate system here? So OA bar is equal to R1 bar, OB bar equal to R2 bar. Let us suppose the first particle starts moving with velocity V1 bar and second particle starts moving with velocities V2 bar. I am going to discuss the condition for the collision of the two particles and also discuss how to find the time interval after which they collide at a point P. That means the first particle moves from A to P in a time interval delta t, and second particle moves from B to P during the same time interval delta t. So at the instant of collision, the position vector of each particle with respect to the origin O will be the same. So for the first particle, you can write OA bar plus AP bar equal to OP bar. That means OA bar represents the position vector of initial position of the first particle, and AP bar is the displacement vector of the first particle, and OP bar represents the position vector of the final position of the particle at the point P. For second particle, OP bar can be written as OB bar plus BP bar. OB bar represents position vector of the second particle denoted by R2 bar. The director line segment BP bar gives you the displacement vector of the second particle. So this equation you can write as R1 bar plus S1 bar is equal to RF bar, which you can write as OB bar, you can write it as R2 bar. BP bar is S2 bar. So here S1 bar, the displacement of the first particle in the time interval delta t, and S2 bar is the displacement of the second particle during the same interval of time delta t. That means after the time interval delta t, the two particles will collide at the point P. Now, if the first particle, suppose, moves with constant velocity v1 bar from A to P, then S1 bar you can write v1 bar into delta t. So here, for R2 bar plus, that means I am equating the first and last here. If second particle, suppose, moves with constant velocity v2 bar, then you can write S2 bar equal to v2 bar into delta t. You arrive at same equation even if both the particles move with constant accelerations, if the acceleration is same for both. In case both the particles move with uniform acceleration, I mean with same uniform acceleration or with the same constant acceleration, then S1 bar can be written as V1 bar into delta t plus half A bar into delta t square. And S2 bar can be written as V2 bar into delta t plus half A bar into delta t square. That means you can arrive at this equation R1 bar plus V1 bar into delta t equal to R2 bar plus V2 bar in delta t. You can write this equation for both the types of problems. That means some problems, both the particles may move without acceleration. That means first particle may move with constant velocity v1 bar. Second particle may move with constant velocity v2 bar. Whereas in some problems, for example in projectiles, we come across examples where you have two projectiles starting from different points A and B simultaneously, which move with the same constant acceleration. So even in such cases, same calculation will be applicable up to this step. That means here the same equation can be written when each particle moves with constant velocity, and same equation is also applicable if each particle moves with same constant acceleration. Here v1 bar and v2 bar are the velocities of the two particles at the initial instant at the beginning of the time interval delta t. So from this equation you can write R1 bar minus R2 bar equal to V2 bar minus V1 bar into delta t. So the time interval delta t is always positive. In case you are given a problem with R1 bar and R2 bar are given, V1 bar and V2 bar are also given. And if you are asked to find whether they collide or not, you follow the same procedure and find delta t. If delta t suppose comes out to be negative mathematically, it means the collision is not possible because the time interval cannot be negative. If delta t is positive, then the collision is possible. So what is the direction of R1 bar minus R2 bar? R1 bar minus R2 bar will be R1 bar minus R2 bar can be written as OA bar minus OB bar. That you can write it as BA bar. Later in relative velocity concept, we'll discuss that V2 bar minus V1 bar represents relative velocity of the second particle with respect to the first particle. So for collision to take place, the direction of V2 bar minus V1 bar should be in the direction of vector difference R1 bar minus R2 bar. That is from B to A. That means for collision to take place, the relative velocity of the particle B with respect to the particle A should be directed towards the first particle A along the line joining the two particles. That means, in general, if two particles start moving with different constant velocities from two different points, then for collision to take place, the relative velocity of one particle with respect to other particle should be directed toward the other particle. That means relative velocity of second particle with respect to the first particle should be directed away from second particle toward the first particle. The same equation can also be written as R2 bar minus R1 bar equal to V1 bar minus V2 bar into delta T. The direction of R2 bar minus R1 bar will be from A to B. You can write R2 bar minus R1 bar means OB bar minus OA bar. That will be equal to AB bar. That means the direction of V1 bar minus V2 bar is same as the direction of R2 bar minus R1 bar in case collision takes place. That means for collision to take place, the direction of the velocity of the first particle with respect to the second particle should be the velocity of the second particle with respect to the first particle. The velocity of V1 bar minus V2 bar should be have the same direction as R2 bar minus R1 bar. That is from A to B. So in case you are asked to find the time after which the collision takes place, you can take the modulus of both the sides of this equation. Again, we discuss the same right from beginning. You can see, consider two particles situated at the points A comma B with position vectors R1 bar comma R2 bar respectively with respect to origin O, that is shown in the figure. Suppose if the two particles start moving with the different constant velocities v1 bar and v2 bar, or with same acceleration. Then the two particles may collide with each other after time interval delta t if the relative velocity of one particle with respect to the other particle is directed toward the other particle along the line joining the two particles. That means here I have given you the conclusion of my previous discussion. Again, I show you the same calculation which I explained just now. In the figure, OA bar represents the position vector of initial position of the first particle denoted by R1 bar. OB bar represents the position vector of the initial position of second particle denoted by R2 bar. V1 bar is the velocity of the first particle directed along the line from A to P. V2 bar is the velocity of second particle. And the two particles collide with each other at the point P. So from triangle law of vector addition, you can write OA bar plus AP bar equal to OP bar. Similarly, for other triangle, you can write OP bar equal to OB bar plus BP bar. So OA bar is written as R1 bar, AP bar is written as S1 bar, means displacement of the first particle. OP bar is written as RF bar, means position vector of the final position for each particle at the instant of collision. OB bar is written as R2 bar, which represents the position vector of initial position of second particle. The director line segment BP bar gives you the displacement of second particle denoted by S2 bar. So if each particle moves with constant velocity, then you can write S1 bar equal V1 bar into delta t on the left hand side. On the right hand side, you can write S2 bar equal to V2 bar in delta t. So from the same equation, considering the first and last of the equations, you can write R1 bar minus R2 bar equal to V2 bar minus V1 bar into delta t. So if you take modulus both the sides, mod of R1 bar minus mod of R2 bar minus R1 bar equal to mod of V1 bar minus V2 bar into delta t. Of course, you can also write otherwise mod of R1 bar minus R2 bar is equal to mod of V2 bar minus V1 bar into delta t. So delta t can be written as mod of R2 bar minus R1 bar by mod of V1 bar minus V2 bar. That means the time after which they collide with each other can be written as equal to initial separation between the two particles divided by magnitude of the relative velocity between the two particles. So time interval after which collision occurs is equal to initial separation divided by magnitude of relative velocity. So in the diagram we can observe that R1 bar minus R2 bar will be from B to A. V2 bar minus V1 bar will have the same direction as R1 bar minus R2 bar. That is R1 bar minus R2 bar is equal to the direct line segment BA bar in the figure. That means relative velocity of the second particle at the point B with respect to the first particle at A directed towards the first particle at A. The second figure I have shown R2 bar minus R1 bar. R2 bar minus R1 bar is equal to the directed line segment AB bar, which acts from A to B. So direction of V1 bar minus V2 bar, same as the direction of the vector difference R2 bar minus R1 bar. That means velocity of the first particle with respect to second particle directed along the line AB. That means away from first particle towards second particle. That means the condition for collision is that the relative velocity of one particle with respect to the other particle should be directed towards the other particle. The time after which collision takes place is equal to the initial separation between the two particles divided by magnitude of the relative velocity between the two particles. Next, I am going to show you some problems on change in velocity, which you can first try it yourself. I am also going to show you the answers. So in this figure here, the same discussion is written here, which I have done calculated previously. AB bar equal to R2 bar minus R1 bar. BA bar equal to R1 bar minus R2 bar. Now shown separately two diagrams. The diagram at the top on the right side has shown the direction of R1 bar minus R2 bar. The diagram at the bottom has shown the direction of R2 bar minus R1 bar. So look at the problems here. In each of the following cases, find the magnitude and direction of the change in the velocity of the particle. That means at once I have shown you 5 problems on the screen. Don't mistake them as multiple choice options. I have given 5 problems here. That means on the left hand side, each problem I have given you the initial velocity. Right hand side, I have given you final velocity. That means in the first problem, the particle has an initial velocity of 10 meters per second towards east, and its direction of the final velocity 10 root 3 meters per second towards north. And you have to find the magnitude and change in the velocity of each particle. You can first copy down these problems in your notebook or on a paper, and you can first try to work out these problems yourself. You can follow the graphical method which I explained in my previous class for finding the difference of two vectors. The same graphical method you can follow here. I am also going to show you the answers for these questions on the screen. In case you get the answers, it's okay. Otherwise, you can see the solutions in my next class. And those students who are able to work out all the problems and those who got all the answers, they can skip the next class and then they can directly go for the other class. See the answers here. Again, I will show you the first problem once. Initial velocity 10 meters per second towards east, final velocity 10 root 3 meters per second towards north. The answer for this question is 20 meters per second, and the direction 30 degrees west of north. You can first copy down the answer also. Then second question, the initial velocity 10 meters per second towards east, and final velocity 10 root 3 meters per second in the direction 30 degrees north of east. For this question, you get the answer at 10 meters per second in the direction 30 degrees east of north. You may copy this answer if you want. Then third question is initial velocity 10 meter per second towards east. The final velocity is 10 root 2 meter per second towards northeast. For this question, you get the answer as 10 meter per second towards north. For next question, that is question number 4. The initial velocity 10 meter per second towards north. The final velocity 20 meter per second in the direction 30 degrees north of east. You may first copy all the answers also along with the problems so that you can try to do them yourself first. And if you're able to get the answers, it's okay. In case you're not convinced with the answers, you can see the solutions of all these problems in my next class. In case you are able to solve all the problems, if you want, you can skip the next class and then go to the class later. So for the fourth question, you get the answer as 10 root 3 meter per second towards east. Then for last question, fifth question, you are given that the initial velocity 10 meter per second towards north and final velocity is 5 meter per second towards south. You have to find the magnitude and direction of the change in the velocity of the particle. So for the fifth question, you get the answer as 15 meter per second towards south.